Hello and welcome back to our lectures on numerical analysis. We are studying cubic splines and we hope to complete that study today. So let me start sharing the lecture slides right away. Okay, I hope you can see these slides now. So we are in lecture number 19 and if you remember we had computed some examples of natural cubic splines and now what we want to do is that we would like to compute some examples of the clamped cubic splines. So in the previous example we had computed a natural cubic spline passing through these 3 points 1 comma 2, 2 comma 3 and 3 comma 5. So these were the three nodes. X0 is 1, x1 is 2 and x2 is 3. x0 is 1, x1 is 2, x2 is 3 and the corresponding function values f of x0 is 2, f of x1 is 3 and f of x2 is 5. So we did compute this natural cubic spline, but now we want to impose some boundary conditions which are the S1 prime. S prime at 1 is 2 and S prime at 3 is 1. These are the conditions that we want to impose and we want to see how the things change. So of course, suppose we have the cubic given by S naught x, which is a naught plus b naught x minus 1 plus c naught x minus 1 whole square plus d naught x minus 1 cube. This is the cubic on the interval 1 comma 2, and the second interval, which is the interval 2 comma 3, we have the corresponding cubic s1x, which is given by the coefficients a1 b1 c1 d1. Then of course most of the conditions for determining these 8 constants are the same as the previous conditions. So if you remember them, those were the conditions where we had the function value at 1, which if you evaluated on S1, S0, it would give you simply A0 and that is equal to 2. The function value at 2, which you could evaluate on both the cubic polynomials, and so it would give you A0 plus B0 plus C0 plus D0 equal to 3, and it also gives you A1 equal to 3. So we have 3 equations so far. We have yet one more equation, which is f of 3, which is the second cubic polynomial S1 evaluated on 3, and that would give you a1 plus b1 plus c1 plus d1 equal to 5. So far we have had 4 equations. There are 8 unknowns. We need 4 more equations and hopefully that will help us get these solutions. So we look at these two equations, which are the equating the derivatives of S0 and S1 and also the next derivative, the second derivative of S0 and S1 at the point which is common for both these subintervals 1, 2 and 2, 3. The point in common is the point x0 x equal to 2. And so at x equal to 2, we have these equalities which will give us that b0 plus 2c0 plus 3d0 equal to b1 and 2c0 plus 6d0 equal to 2 times c1. This is the double derivative. Okay, so we have 2 more equations with the 4 equations earlier. These two, we have now a total of 6 equations, and now we impose the boundary conditions. Those are the new conditions. S0 prime at 1, which is the leftmost endpoint. This is b0. If you compute the derivative and put x equal to 1, you are going to get b0. We have that this derivative value is 2. So b0 is equal to 2. And we have that s1 prime at 3, the final endpoint, is equal to 1. So it gives you b1 plus 2c1 plus 3d1 is 1. Now, of course, a0 is known, a1 is known, now b0 is known, and the remaining various values can be solved. So for instance, c0 plus d0 will give you an equation which is equal to 2, 3 minus 4. So this sum is equal to minus 1. And then there are some more conditions which can be obtained from here. Further, we have some more conditions which can be obtained from here. So solving all these equations together, we get the clamped spline as the set of 2 cubic polynomials given in the following way. So these are the two clamped, this is the clamped spline given by two cubic polynomials for the intervals 1 comma 2 and 2 comma 3 respectively. So this is also something that we have been able to do. So earlier we had computed the natural spline, and where we did say that the number of equations agreed with the number of constants that were to be determined, and then we alluded to a linear algebra proof which we did not cover, which would guarantee the existence of the natural spline. Similarly, we seem to have a similar result for cubic splines. Also, let's do one more example. But okay, so before going to the second example, we would like to establish this theorem on the existence of splines. I realized that I had never stated it even for the natural spline. So let me just have this result stated for once and all. So what it really means is that the set of equations that you get, not just the set of equations which you have when you evaluate the polynomials with their various values and their derivatives, but also the boundary conditions, they will lead to a unique solution. And this second proof for the clamped spline also involves linear algebra, and we are going to skip that one also. These statements read as follows. So let me once keep the statements here for the record. The statement for the natural spline is that if you have a function f which is defined on x naught less than x1 less than xn, which is b, x naught is your a, then on these nodes the corresponding function has a unique natural spline, cubic spline, of course. Okay, and if you are looking for the clamped cubic spline, you have to only add the condition that your function be differentiable at a and b, so that you know the derivative values at a and b. So once again, the second statement reads that if your function is defined on these n plus 1 nodes, a equal to x naught less than x1 dot 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 less than xn, which is equal to b, and you have some information on the derivative values, then this function will admit a unique clamped cubic spline interpolant S on the given nodes x naught up to xn. So this once and for all gives us the existence of natural cubic spline as well as the clamped cubic spline. Okay, so now we go towards solving one more example, which is repeating actually of our second example for the natural cubic spline, which was the e0 e power 0, which is 1. So 0 comma 1, 1 comma e, 2 comma e square, and 3 comma e cube. So this was the example that we had actually looked at when we computed the natural cubic spline. Here we are going to have the boundary conditions which are also given to us because the derivative at 0, of course the function fx is e power x, its derivative is itself. So the derivative at 0 and derivative at 3, those are going to agree with the function values. So the derivative at 0 is e power 0, which is 1. Derivative at 3 is e cube, which is e cube. Okay, so with these, we will write the cubic polynomials as Sj, which are given by constants Aj, Bj, Cj, and Dj. And these Sj are valid from xj to xj plus 1 when you let j go from 0, 1, and 2. Okay, so we have 3 cubics given by these 4 constants for each cubic, and so you have a total of 12 such constants. And if you remember, we had a matrix equation for them. We will have a similar matrix equation, but once again, just as we have done the previous example of cubic splines, here also the most of the values don't change because they are related to the only change happens at the boundary conditions. So whatever the inside values we have, those are not going to change. So those values remain the same. You are going to have n equal to 3. You are going to get hj equal to 1 because 0, 1, 1, 2, and 2, 3. They are equally spaced nodes. So hj is 1 for all j. You have a naught is 0, a1 is e, a2 is e square, and a3 is e cube. I spot a mistake here. A0, which is the function value at 0, that has to be 1. So I'll make that change. A0 is 1, A1 is E, A2 is E square, and A3 is E cube. And together with the information that the derivative at 0 is 1 and derivative at 3 is E cube will lead to the matrix equation which is written here. If you remember the matrix equation for the natural splines, you would perhaps remember that the second entry in the first row was 0. Similarly, the second last entry in the last row was 0. But here we will actually have all the diagonal entries, possibly all the upper diagonal entries and all the lower diagonal entries also. But we will not have any other non-zero entries. So we get this matrix equation where you have a nice matrix multiplied by the column consisting of the values of Cj's which are to be computed. And finally, we have a column matrix which gives you some constants. So we can solve this. We will actually write down this solution. So each of these can be written in terms of various combinations of constants E square and E cube, but I will not write down that explicit expression. I just write down their approximate values by doing those arithmetic. So C naught is 0.44468, C1 is 1.26548, C2 is 3.35087, and C3 is 9.40815. So these are the values of Cj's. We put these values back and determine the remaining constants, which would be Bj's, and then finally you have Dj's. Aj's are already known, and together with all these values, we will have the corresponding cubic polynomials to be these polynomials. The very first one is the polynomial which is valid for the interval 0 to 1. The next is valid for the interval 1 to 2. And then we will have the final polynomial which is going to be valid for the interval 2 to 3. So this is what we have in case of the cubic clamped spline interpolant for the function f of x equal to e power x for the interval 0 to 3. Okay, so one nice thing about cubic splines is that you can use cubic splines even when you don't really have a well-defined function. So in the last example that we have just looked at, we actually looked at f of x equal to e power x. But you may not even have such a function, and therefore natural one is more useful. And then there are some more ways to compare them. So for instance, when we computed the cubic spline interpolant for e power x, we indicated that there might be an application for that using there might be an application of the cubic spline in using computing the integration. So we have 0 to 3 integral 0 to 3 e power x dx, and we indicated how we can just split it up as an integral 0 to 1 s naught plus integral 1 to 2 s1 and integral 2 to 3 s2. And because s0, s1, s2 are polynomials, it is not typically easy to compute those integrals, and that is one application of natural splines. But now we have also computed the cubic splines, and here is a nice opportunity for us to compare how these two integral values behave. So in fact, the actual value, which in this case can be computed explicitly because we have a very well behaved and well understood function e power x, but in general you may have a function which may not be so well behaved, and therefore the cubic splines, whether natural or clamped, will come to your rescue in computing the integrations, the numerical values of the integration. So here the actual value of this integration is about 19.08. And the natural cubic spline will give you the value 19.55. So this is roughly the departure is 0.5, right? So it's roughly 0.5, whereas the clamped cubic spline gives a much better approximation. It gives you a much better answer. And this is not surprising at all, because the clamped spline is superior. It gives you a much better approximation since your boundary conditions are also exact. The natural boundary conditions are only giving you that the s double prime at 0 and s2 double prime at 3 or S double prime at 3, these are both 0. That is your natural boundary conditions, while the actual values are 1 and E cube. So clearly, because you are not taking the correct values, the natural cubic spline, while it's not off by a very large margin, still it's not giving you better values, and therefore cubic splines which are given by the clamped boundary conditions, they are typically more useful. So this is something that we have also said earlier, that although it is very natural to take the natural boundary conditions or the free boundary conditions, because the derivative values may not be available. But whenever the derivative values are available, we will always go for clamped cubic splines because they give you a much better approximation. And we come back to our example that I think we have done maybe 2 lectures back, which is that where we did not really have a well-defined function, meaning there was no formula for the function, but we had only used a large data because we wanted to do something which is very physical in nature. So we have no description of the underlying function, but we will apply cubic spline. So for instance, if you remember this flying duck, suppose we want to trace out or understand the top profile of this flying duck. If you remember, we had done this example for interpolation, for Lagrange interpolation, and we saw that the Lagrange interpolation was giving you large errors. We will try to see whether cubic spline gives you a better approximation. So this is our duck and we want to understand the top profile. So we are going to have those same 21 data points that you remember very well. And after you put the grid and choose those data points with the understanding that wherever the curve changes rapidly, we will have more data points to get a better approximation. And whenever the change is not so rapid, then we will not have those many data points. Just for the sake of record, I will write down all these 21 points and their function values. And we are now going to compute the cubic spline. But it's a natural cubic spline because we don't have any information about the boundary condition. So it's the natural cubic spline for our data for understanding the top profile of the flying duck. These are the cubics. So there were 21 points. You know, in each column here we had 3 points and there were 7 columns. So we have 21 nodes and therefore we are going to get from 0 to 20, we have 21 nodes and then we are going to get 20 cubic polynomials opposed to the degree 20 Lagrange interpolating polynomial that we had. So opposed to that, here we have AJ, BJ, CJ, DJ. There are 20 such sets. And I will just give you this solution that, you know, maybe you can sit down and check some of these. I think it would be nice if some of you did try and solve some of these equations. You may just choose, say for j equal to 6, you may choose and then try to solve the things. You would know what is the value of the function S6 at the initial point, at the end point, and you have some more data about the derivatives and so on, and maybe with S5 and S7 you will be able to do some computation. So I have told you that the matrix will be a tri-diagonal matrix. It's called a tri-diagonal matrix. You have the diagonal matrix where you have only the diagonal entries, but our matrix will have diagonal entries, a super diagonal entry, and a sub-diagonal entry. So it's a tri-diagonal entry, and so whenever you are looking at one particular equation, you will have maybe 3, not more than them, entries to look at. So if you just check for one such thing and try to solve, you will see that this is indeed a correct solution. So you have AJ, BJ, CJ, DJ for all these 20 cubic polynomials. And once we put this back in, superimpose it on the top of the flying duck, then we see that it is almost identical. And this figure actually tells you about it. You will see that there is some change somewhere, but the change is very minimal. Meaning if we blow this up, if we zoom in inside this picture, then we will perhaps see the change. But otherwise, this looks like a very good picture. So this is what happens when we are looking at the natural cubic spline. Of course, we could have used clamped cubic spline to approximate this curve. We would need, of course, the two endpoints derivatives, but once you have those derivative values, then you may talk about clamped one. But just to bring you back to the data where we have superimposed the cubic spline, the natural cubic spline on the flying duck, we see that it's nearly identical. Therefore, even if you had information about the derivatives at the ends, it would not give you too much improvement because the natural cubic spline already is very good approximation to the curve that we wanted to identify. There is also another question that one may ask. Can we now look at the bottom profile of the bird and can we try to understand it using either a spline or an interpolation or maybe something else? So there are several problems here. The problems are, first of all, that it's not even a function. We will see the picture of this flying duck once again. In the next slide, you will see that the wing that we see has come a bit forward. The lower tip of the wing is forward, and therefore there are points where this lower profile will give you more than one function values, and then it's not a function. Meaning these are some of the very basic definitions that you will perhaps have to brush up, that for a function to exist for a given point, there will have to be a unique function value. You cannot have more than one function values and then call it a function. Okay. Moreover, this wing especially that we see is not even a smooth curve. So the curve is not smooth, whereas the top profile was a nice smooth curve, although it had some irregular shapes, but it was a differentiable curve all through. The bottom profile doesn't appear to be smooth. So these are the problems. You may ask whether we cannot attack such a kind of a problem, we cannot deal with these kind of problems at all. No, that's not true. In mathematics, there is an answer for everything, and if there are no answers, then the questions are more interesting. So there is a way to tackle such a situation. There is a different approach which we will need, but it will not be dealt with in our course. There are something called as Bezier curves which are going to be needed, and of course when you have more function values, then you are going to break your curves into subsets, such that for those particular subsets you have a unique function value. So let me go to this picture once again, and we see that this lower part of the wing has come slightly ahead, and therefore for the point 5, for instance, you have one function value which is above the x-axis, another function value which is below the x-axis, but it's the upper part of the wing, and then at the bottom of the wing you have one more function value. So what one could do is that you could look at the graph starting from the nose of or the beak of the bird and go all the way up to say 5.6, and that gives you the profile which seems to be at least piecewise smooth. Then you look at the part where the wing starts and take only the top profile of the wing. So that again gives you some nice function. There are no repetitions here for function values. And once you reach the lower part of the wing, that's where you end your second set. And then from the lower part of the wing all the way up to the tail of the bird, that will give you the third part. So you can divide this problem of approximating the lower profile of the duck into three problems, where the lower profile itself is divided into three subsets for various points of the x-axis. And so this is what is called parameterization of the curve. So you break your curve into several parts and study each part separately. And then there are other approaches which could be used to solve cases of non-smooth curves, but we will not go into them. This is where we are going to stop. I will end this lecture by discussing the error. So whenever we have interpolation, there is error always, and the error formula can be written down here explicitly. So suppose you have a function which is 4 times differentiable on the closed interval AB, and suppose the fourth derivative, which is now a continuous function, it is bounded on the interval AB by this constant capital M. Okay, so there is this upper bound, the maximum, because you are looking at a closed and bounded interval. It's not supremum, it is maximum. You have this capital M, which is the maximum value of the fourth derivative on the interval A to B. Then for the clamp cubic spline interpolant to the function f with these x0 up to xn, for all x in AB, the difference between the function value and the spline value is at most 5m upon 384, and the maximum of the node distances, the maximum of the distances between consecutive nodes. We had called these hj, if you remember. So it is the maximum over j, hj power 4. There is a fourth power also. Okay, so this is the error formula that we have for clamped cubic spline. There is indeed an error formula for the natural cubic spline also, but it's slightly more difficult to express. And this is quite understood because the natural cubic splines are more error prone. There is no boundary condition which is given to us, so they are more error prone. Their errors are worse, and therefore to write down the formula which exists, but to write it down is not an easy thing. So we will not write down that formula also. And with this, we come to the end of our third theme, which is the theme on interpolation. If you remember, our first theme was on machine arithmetic, second was on equations in one variable, and now this completes our third theme of our course on interpolation, and we will begin in the next lecture our fourth theme, which is the numerical integration and differentiation. So that's where we stop today for in this lecture, and see you in the next lecture. Thank you.